So I wanted to start today by I'll probably start today by considering Bayesian linear regression. So last time we saw standard linear regression and we looked at maximum likelihood in that type of model. This time what I want to do is do a bit of review of the Bayesian stuff that we talked about in the first couple of weeks and sort of motivate it in the context of regression and try and explain why it's necessary. So just to give a couple of examples of data sets that I'm aware of that people have used regression for. I mentioned one thing on Tuesday, but predict the quality of meat given some spectral measurements. So there's this Tecator data set which is in Denmark. So I guess Denmark exports a lot of pork, a lot of bacon, and they automatically want to try and detect meat quality. So they have some measurements and they try and predict the meat quality. So that's the regression problem. If you've heard of radiocarbon dating, so radiocarbon dating, there's you're trying to estimate the age of something by the quantity of carbon-14 it contains. So there's two things. There's the carbon-14 age, but that actually maps differently onto real age. So they know, for example, from tree rings. So you can get a tree ring record going all the way back thousands of years, and that gives you a very precise aging because you can sort of match up different trees. Basically, each tree grows a different amount per year. So you get this unique profile depending on how warm the year was across lots of trees. And they line all those up and they go back thousands of years. But you also have carbon inside the trees. So you can get a carbon date from each of those trees as well. And what they find is that the carbon-14 date doesn't actually match the age that you get from the trees. So there's a calibration curve. So you take the carbon-14 date and you translate it to real age. So that's another regression problem. A further one was an early version of backgammon. Intelligent backgammon player was basically done by, and this is also true for an intelligent Go player, although the best Go player doesn't work like this anymore. But they were done by experts looking at certain board positions and scoring moves, giving a score of the quality of the move. So you could take various moves and the expert scores which is the best move. And then you can do a regression from what's on the board to the expert's quality of score. So people have tried that sort of thing as well. So those are some sort of examples of what people have done with regression. So what I wanted to talk about today is Bayesian regression, and I want to motivate that by looking at underdetermined systems. Well, what do we mean by underdetermined? Well, we actually talked about the fact that regression's overdetermined a little bit last time, so I thought I'd just sort of emphasize what we mean by that. So a straight line, as we see in this plot, is defined uniquely by 2 points. Yeah? So you don't need any more than 2 points in if you're building the line with one input and one output, as in this case. You don't need any more than 2 points to define the line, and if you've got that point and that point, what you find is you find the intercept of this line on the 0 point on the x-axis, which is in this case at 4, and you call that c. And you find the gradient by taking the difference between the y values of these 2 points, which in this case are the target values, so we've called them t, and the x values between these 2 points, and you just compute the gradient. And if you write down the y equals mx plus c, and substitute in x1, y1 equals mx1 plus c, and y2 equals mx2 plus c. You have two simultaneous linear equations, and these are the solutions. What I'm showing you here is the solutions you get to that. So you can determine a line with 2 points. One of the things we talked about last time was the fact that when they were first trying to fit models, sort of just post-Newton, in the sort of period of Laplace and Gauss, they had this problem that they were writing down these simultaneous equations with a number of unknowns. So you have two unknowns in this case and two observations, and you can fit it exactly. But if you have more observations than unknowns, say we introduce a third point here, if we make the same computation for this third point, so if we were to compute m but with this point and this point, we would get a different gradient. And if we were to compute n with this point and this point, we would get a further different gradient, yeah? And same for c. So that was kind of confusing, and then to solve that, they introduced the idea of having a noise model. So this is the basic point, that you've got two unknowns and two observations. You only need two equations to solve it, and you can now solve for m and c, and the solutions are on the previous slide. Now in this case, we've got an overdetermined system if we add an additional observation. And you can't solve those three equations simultaneously. So what you have to do is add a corruption. And the corruption is different in each case. So the idea is the corruption is coming, it's unobserved, it's latent, it's coming from measurement error. And the reason you're observing these different things is that the underlying model is correct. There really is an M and C, that's the theory, although often that won't be the case. And then there's you're observing some corrupted version. So that's an overdetermined system. And the way we've resolved the problem with the overdetermined system is by introducing uncertainty. Uncertainty of the measurement error. And that's the way they did it as well. Okay, so let's go the other way. What about two unknowns and one observation? How do you fit a straight line through that point? Okay, that's a different thing. Now there's many straight lines that could go through that point. So what I think I would argue as someone who practices, and I don't mean practice as in practicing the piano, I mean practices as in it's what I do, Bayesian approaches, is that you might be interested in all lines that are consistent with that point. So if you have, oh dear, I know what's wrong there. Sorry. So if you have a graph like that, so you've got one point, then clearly any line that you draw, all these lines are plausible, yeah? They're all valid. And they don't even need to pass exactly through the point because of measurement error. So they could pass slightly below. Yeah? So that's kind of confusing. But can we do anything with that? Well, it turns out you can. And that is exactly what Bayesian methods are about. What's happening here is certain parameters are consistent with this cross. So although we don't know what the actual exact values of these of the gradient and the offset are in this case, what we can do is we can, if I start drawing blue lines down here, I mean, if you've got an idea of what the noise is, you might say that these are perhaps less likely, yeah? Well, even if you don't have an idea of what the noise is, you might believe that something closer to the observation, you might believe in lower noises. So that line over there, less likely. A line down here, less likely. So there's a family of lines that you might believe in as being more likely, and a family of lines that you might believe in as being less likely. So how do we represent that belief? Well, we're going to represent it through probability distributions. That's the very elegant part of Bayesian inference. Okay. So, and also historically, well, you know, some people find it controversial, and I'll talk a little bit about why they do that. So the Bayesian approach. So likelihood for the regression example, the multivariate regression, actually I've put a phi in here. You'll see why I did that. That's a mistake actually, but you'll see why. There's a phi there. Think of that as an x for the moment. So the suggestion was to maximize the likelihood. We did this last time. We found an optimal value for w, given this likelihood and some observations t and x in this case. So that can be done with gradient-based optimization of the log likelihood, but the alternative approach, the Bayesian approach, actually involves integration. It's quite funny actually, because in one approach you're looking to solve the problem by differentiating something, and the other approach actually involves integrating something. So what we're going to look at today is a little bit of multivariate integration. But again, it's quite simple. It's not something to get worried about. Multivariate integration can get very difficult, but the type of examples we'll be using will keep it very simple. So instead of, what we do is instead of considering a point estimate for W, we look at the expectation of the likelihood under a range of believable parameters. So you have to start out by laying down a prior distribution over parameters you believe in, and then you look at an expectation of your likelihood under those prior distributions. And then you can get a posterior distribution of parameters that you think are reasonable. And through the posterior, you can have a look at what sort of lines you think are sensible. What I'm going to try and do at some point, and probably make an idiot of myself, is I'll try and do some stuff in Octave. I was going to do it in Python, but I'm more familiar with MATLAB, so I'll do it in Octave to try and sample things once we've shown what the setup is. Okay, so now a lot of people are confused about the term Bayesian, and I would say this is true of a lot of people in machine learning too. So, but I just want to highlight some point here. When we do this, we're taking a Bayesian approach to data. Now, I want to make it clear that Bayesian approach is not named after Bayes' rule. It uses Bayes' rule, but it's not named after Bayes' rule. Bayesian approach is a philosophy for dealing with parameters which some people disagree with. You can't disagree with Bayes' rule. It's mathematically proven. There's no subjective nature to Bayes' rule, right? So naive Bayes, for example, is using Bayes' rule, and the Bayes means Bayes' rule. It doesn't mean Bayesian. It's not a Bayesian approach, not unless you start treating the parameters in a Bayesian way. Bayesian approach is about a certain approach you're taking to parameters. That uses Bayes' rule, it computes similar posteriors, but the term Bayesian is referring to the treatment of parameters as stochastic variables. Okay? And I'll try and explain what that means, and maybe hint at why maybe statisticians thought that was controversial. So for early statisticians, about 80 years ago, this was considered very controversial, and this fellow called Fisher, he actually coined the term Bayesian as an insult to people who were using what they at that time called inverse probability, which is a much better name, inverse probability, for what you do. So I want you to just recall, so this is separate from regression, but this is where the controversy of Bayesian approaches start. So I want you to recall the Bernoulli distribution that you've actually seen used for logistic regression, yeah? So it's a classification distribution. And it was defined by Jacob Bernoulli, who talked about, as I understand it in his paper, he talked about an urn. So I've drawn it, this is my urn, with a different number of red and black balls in. And the idea was, the test is you put your hand in there, you pull out a ball, and the ball's either red or black, and you're randomly picking a red or a black ball. But the probability of the event itself is not random. Yeah, because there's a fixed number of black and red balls. This is epistemic uncertainty. So it's an actual value, yeah, but you just don't know it. So maybe someone else knows it. So it's knowable, but you don't know it. So it's an actual real parameter. It's a fixed value. Now, don't worry too much about the functional form there. That's the real point there. So this is what Thomas Bayes did, and this is why they call it Bayesian. He wasn't thinking in Bayesian terms, but this is why they call it Bayesian. Just as it's a nice example to keep in your head of the difference. So he introduced the Bernoulli distribution. I don't know if he knew about Jacob Bernoulli. He's after Jacob Bernoulli, so he may well have done, but he chose to introduce it in this way. He talked about a table where you roll a ball and it bangs from side to side in the table, and the idea is the ball lands in a uniform position between the left and right hands of the table. So think of a snooker table or a billiard table, and someone just bangs a ball from side to side. Now that probably isn't a fully uniform random process, I don't know, but let's assume it is. And so this ball lands on the table uniformly from one side to the other. Now, think of another ball that someone else, so let's say I do that experiment, I do that ball, and I hide the result from you. But what I do allow you to do is I say I'm going to run another ball and do the same thing. And as I do the other ball, it lands either to the left or the right of the first ball. Okay? Now this is a Bernoulli distribution. Yeah? So this is the probability of it being on the right. We can think of right as success or left as success. So we've got red and black balls, but they have very different purposes here. So a second ball, we can do it again. And then obviously because this ball's quite a long way to the left, most of the time it will be to the right. But on this occasion I did 7 random samples and the 7th one came on the left. Now if we kept doing that, then eventually you would be able to identify exactly where that first ball had gone. Just as if we keep doing that with the urns, if we keep sampling, then eventually you'll work out how many red and black balls are in there. But the point is here, the parameter of this Bernoulli distribution is a stochastic variable. It's sampled in exactly the same way that we're sampling future variables as well. And Fisher hated that because they believed in models that had deterministic parameters and didn't like this stochastic interpretation of variables. But that is exactly the Bayesian interpretation. Now, they consider that very controversial. I think it's a dead argument, and Bayesian statistics are really well, very, very widely used. There's a lot of other complexity to those arguments, which I won't talk about. But here's my example of why. This is sort of what it comes down to. This occurred to me while I was watching England playing rugby against France, and I was cycling when the match was on because it was on early in the morning, so I recorded the match, and then I came back and I started watching the match well after it was finished. So I avoided watching TV and I avoided clicking on the internet, so I didn't know the result. Now, as far as I'm concerned, sitting watching that match, it's just as exciting for me as if I was watching it live, because I don't know the result. But this is the separation between epistemic uncertainty and aleatoric uncertainty. Because if you were watching the match live, that is aleatoric uncertainty. No one can predict that result. It's overly complex. I mean, in theory, it might be possible, but because of chaotic things and all the stochastic things that go on, no one knows that result. Whereas when I'm watching it later, it's epistemic uncertainty. And in fact, in this case, England played so rubbish that I got sick of watching it and went to look at the result on the internet, which is something you can't do if you're watching it live. But if you do maintain that pretense, and if you ever do this yourself, you watch it on Sky Plus, if you maintain that pretense that you don't know the answer, the excitement of watching the match is just as good. Okay? So there's no, as far as you're concerned, there's no difference between these two approaches. But philosophically, there is a difference. One's knowable and the other is unknowable. One, you have to wait for the answer, right? No one could tell you the answer at that precise time. The other, you can just go and look on the internet, or you can ask a friend or something. So that's the difference between epistemic and aleatoric uncertainty. And Bayesians treat both uncertainties with probability distributions, whereas non-Bayesians won't treat an epistemic uncertainty with a probability distribution. They don't like that. Okay. So simple Bayesian inference, we've already been through this before, but just to review it again, we've got these different components. We've got the likelihood, which is the relationship, which is often, people think of that as our model. I actually prefer to think of the whole thing as a model, likelihood and prior. But people think of the likelihood as giving the relationship between your parameters and the data. And then you've got a prior, which is a distribution over your parameters that you put in place before you do inference. The marginal likelihood is the result of integrating out those parameters. And the posterior is what gives you parameters that are consistent with the data and your prior. Yeah? So this operation is what we're going to go to. So Bayesian regression. I don't know what's happened there. Interesting. Don't know why there's a 0 there. I think I used the wrong. Okay, so this is supposed to just be a 0 mean Gaussian. So prior distribution, what we're going to do is we're going to do just a linear regression. Let's see what we got on the next slide. Yeah, okay, let's look at that. So we'll do a linear regression as we've been doing before. Here's our likelihood, and it's a likelihood over data set size n. So we're summing over, in the likelihood comes out, we've got this n over 2 appears, and you get the sum over n, as we did in the maximum likelihood before. But now we're going to introduce this prior over c squared. And what we've said is that the prior is where the intercept is on the y-axis is 0 mean, so you see it's just c squared, there's no mean there on the prior, and it has variance alpha 1. So this is before you see the data, you're basically making a statement that you think that the intercept of that line is going to be centered on 0 and have some variance. It could be a very large variance. I mean, if you don't know anything about the scale of the data, you know, if someone's giving you things in meters or kilometers, this actually affects the prior. So this is one of the difficulties of the Bayesian approach. How do you get this prior? So people try sometimes to choose something that's quite uninformative, so they might try something which has quite a large variance. You can't have an infinite variance, though, because that's not a probability distribution anymore. Sorry, a probability distribution anymore. Okay, so I think next. So what's the process? Well, there's 3 components we're interested in. There's the prior and the likelihood they're defined. Now, fun thing about Bayesian inference is once you define the prior and the likelihood, everything else exists, actually, because this is a simple mathematical relationship between them. The posterior immediately exists because you know that the posterior is the prior times the likelihood divided by the marginal likelihood. It's found in this form. There's sort of no learning. Once you've said your prior and your likelihood, bang, that's it. But actually you have to do the integration. To actually find this posterior is sometimes very difficult. It's often intractable to find the posterior. So for sort of complex models, for very complex models, you just can't do this. But for linear regression and the stuff we'll look at, you can do this. And then there's this marginal likelihood here as well. So the marginal likelihood is the probability of the data with that parameter disappeared, yeah? And that can be used for model selection. It's quite an important quantity. So to get that marginal likelihood, you have to do this integral, though. And this is the nasty bit. Integration is harder than differentiation. If a function, I mean, oddly, okay, if a function is differentiable, if you can differentiate it, you always can differentiate it, if you see what I mean. A computer can do it. There's a series of mechanical actions that you can take on the functions to just derive the derivative. Even if the integral of a function exists, you might not be able to find out what it is. So there's many functions you can write down, you know the integral must exist, you can compute it numerically, even in 1 dimension, but you can't write it down. There's no form, there's no clean form for it. You have to do some sort of lookup table. I guess maybe that's because, I don't know, that differentiation is a very local operation, yeah? It's occurring at the function, it only depends on the function at that point, because it's the gradient there. Integration is a global operation, it depends on the entire function, so maybe that's why it's more, I don't know. So what we often do, and here's our trick, we're never going to integrate anything in any of the stuff, even though we're going to solve for the integral. Now how are we going to do that? Well, we're going to use one of the properties of probability. This is the big Bayesian trick, that you know that the thing on the left is a probability distribution. So what you can do is just, okay, so the thing on the left is a probability distribution. The C, it's a probability in C. C doesn't appear on the bottom because it's been integrated out. It does appear on the top. But you can ignore the bottom because you know this is a probability distribution and you know that this term must be just such that this distribution is normalized. Once you've got the functional form of the distribution, you just need to normalize it. That's where you're doing the integration because you know about certain distributions. You know what a Gaussian looks like. I mean, this is true for many distributions. We'll just look at the Gaussian. But you know what the Gaussian looks like. You know what the normalization constant looks like. Someone computed that normalization constant by integration before, and you just use your knowledge of that. In some sense, it's like knowing what the indefinite knowing what the definite integral is of that function. You just memorize the form of the probability distribution. So you don't need to look things up, and in fact, everything we'll do will keep everything Gaussian. So all you need to do is remember the form of the multivariate Gaussian, and you can always do these integrals. Nothing hard happens. What does happen is you end up having to convert this top bit here into the right functional form. So the way we always express Gaussians in this way, yeah? So I mean, there are other ways of expressing Gaussians, but we'll always express them as a quadratic form where we factorize it out. So we complete the square. So the first thing we're going to do in a moment is we're going to multiply out this likelihood, yeah? And once we multiplied out this likelihood, that's not normally the form we write the Gaussian in, but we'll multiply it out and combine it with that, and then we'll rewrite it again in a form like this. And once we've got it in this form, that top bit in this form, that tells us what this Gaussian must be. And we'll just use that trick. So we're going to do it first here for univariate. And that's just in case I get lost, but I'll try and do it live, as it were. Okay. So I kind of like it when it's black. That takes a little while to do. So one sec, sorry. Let's do a new one. Paper color. Other. Okay. Oh, paper size. Okay. So, now let's see if I can remember those likelihoods, etc. So, what we said was we've got the likelihood of our data. I've got it in ruler, which is probability of t, where t is the vector of all data, given x, where x is the vector of inputs, c is the offset, m is the gradient, and sigma squared is the variance of the noise. And that's going to be Gaussian. But because it's the product of all the data points, we end up with this. Normally, a univariate Gaussian would just have a square root, but this is actually a multivariate Gaussian because it's the product of all data points. And then so this is what we maximized last time. Oh, sorry, need the sum in there. And what I'll actually do is I'm going to bracket this little term here because that makes it easier to think about that term separately. And then we've got a prior distribution, which is Gaussian again. Now this is a univariate thing, so it's got a standard Gaussian form. And we call in the variance in this case, we'll just call it alpha. Okay? Now the thing that we want to know is, well, it always starts in the same position. We basically want to multiply these two together. But the way we'll do that is we're going to look at the log. Because the log, well, we're going to look at these exponents. So multiplying these two together, of course, is just going to cause the exponents to be summed. And that's where we're going to do all our work. Because what we want to do, we know that the posterior is proportional to this term here. Yeah? And so what we're going to do is we're going to find the functional form of that term there in terms of c. And then we're going to normalize it. So the functional form of that term there, c only appears in this exponent. And the way it appears, if we write down what the exponent's going to be, and I'm going to write it multiplying out the squares, yeah? So minus 1 over 2 sigma squared sum I equals 1 to n, and this bracket term squared. So I just want to keep those guys together. So doing this, it feels like being a celebrity chef, you know. I should have, here's a derivation I prepared earlier. So I'm going to keep those guys together like that. And then I get, from the quadratic form, I get 2 times, but basically I've got a factor of half on the bottom, so I'll just cancel that with what was the factor of half there. So I'm not putting in the factor of half there. Sum of I equals 1 to n ti minus mxi times c. That's right. So that's just the term for multiplying that by that term and timesing by 2 in the quadratic form. Now I get a term that's c squared. So that's minus 1 over 2 sigma squared c squared. And then I need the term from the prior. So I also have a minus 1 over 2 alpha c squared. Now the trick to these things, sorry, you're absolutely right. Very good. N over c squared. Yes, so because c squared appears n times, then you basically get, and there's no index I here, you just get a multiplication by n. Thanks for that. Okay, so the idea here is we want to collect the terms that affect c squared. Why is that? Well, because we're trying, what you're doing here is you recognize that the result of this product is going to be a quadratic. And any distribution that is e to a quadratic must be a Gaussian distribution. So we're trying to rewrite the Gaussian distribution, we're trying to write this quadratic back into the Gaussian form. And to do that, we have to complete the square of this quadratic. But the first thing to notice is it's very easy to pull out the variance. The first thing you always pull out is the variance. When it's multivariate, which we're going to do in next lecture, you pull out the covariance first. Yeah? It's easy to pull out the covariance. So what is the variance here? Well, the variance is those terms that are affecting c squared, but 1 over those terms. Because in a Gaussian, as we've seen here, look, in this case here, the variance just affects c squared. Yeah? So to find the variance of the posterior, we just need these 2 terms here. So the variance of the posterior, we need to rewrite those as in the right form. So this is what we're seeing. What we want something in the form of is, let's see, if I call that, if I call it squiggle, which is a variant on sigma. What we want something is in that form, c squared. But what we've got something in is in this form. So what we know is that this variance must be equal to n times sigma to the minus 2 plus alpha all to the minus 1. Why is that? Because I can collect these terms. I can just write half minus a half of n over sigma squared plus alpha, sorry, 1 over alpha, and I've missed the minus 1 here, plus 1 over alpha, yeah, like that, times c squared. But that's not the variance, that's a precision, which is the inverse of the variance, so the variance is that inverted, which is what I've written here. Yeah? Make sense? So doing these integrals is just a matter of spotting what these terms must be. Once we've defined what the variance is, we now need a mean. So we need to complete the square on this mean here. So this is the linear term affecting this mean, right? So if I were to write down, so I'm starting to form the form of this variance. So I'm trying to get this density in the form c minus mu 1 over 2 sigma squared. I'm trying to get this guy here in that form. Now, one thing just to note in passing is that this term is irrelevant. Yeah? Because it doesn't contain c. And of course, the other thing you're allowed to do, when you should know this from being able to complete the square before, is you're allowed to generate as many terms like that as you like. So in order to get this mean out, what we need to do is we need to realize, okay, so if you were to multiply that bracket out, you would get a term of the form 1 over nu squared times c mu. So we need to make this thing here into that form. So that isn't an equals there, sorry, that's the linear term. We would get, this would equal 1 over nu squared c squared minus 1 over nu squared c mu minus 1 over nu squared mu squared. Yeah? So this term is already matched to that term by our choice of nu squared. Yeah? We've just got to match the other term. And to match the other term, what we need to do is we need to set mu equal to nu squared divided by sigma squared times the sum I equals 1 to n of ti minus mxi. And I think if you substitute that into there, you'll see that that nu squared cancels with that nu squared, and then you just recover 1 over sigma squared, sum of I equals 1 to n ti minus mxi, which is exactly what we've got in the original. So this is the univariate case, and what we've recovered, or what I'm trying to explain to you, and I hope it's clear, is that P over C, sorry, you probably want that still on the screen, yeah. P over C, given, what is it given? T, x, m, sigma squared, is a Gaussian form. Now, this is the normalization. We haven't computed it. We know it, though. We just know it, because we know that Gaussians are always normalized. So this is the var sigma there. So it must have that normalization constant, or else it wouldn't be a probability distribution. And this is the term we've matched up at the top, c minus mu, where we discovered that c squared is equal to n minus 1, sorry, n sigma minus 2 plus alpha minus 1 minus 1, and mu is equal to Now, a couple of things to note about this. Number one, we haven't got rid of n. It's another parameter. So we would actually now have to place a prior over n and integrate that out as well. I don't want to do that because I just want to go multivariate straight away because it's easier. What else can we notice? So if we were to do the maximum likelihood solution for this, as we did, what we would find is that the maximum likelihood solution is that c hat is equal to go away, divided by n. Yeah? In fact, if you think of this distribution is over t, but if you ignore the mx, then you just see the maximum likelihood solution for the bias is equal to the mean of the Gaussian, yeah, as we've seen several times before. And now we just have the mx appearing in there as well. Now compare that to this mean of the posterior. There's a similar form there already, isn't there? Because look at that guy there, and look at that guy there. Now, and then, because there's an n in here, and it's to the -1, and the nu squared, the var sigma squared's on the top here, there's sort of this term is behaving a bit like n. In fact, let's look a bit closer at that term, and we'll see that you can rewrite it as, if I divide through by, let's get this right, that's equal to 1 over sigma squared n sigma squared, sigma to minus 2 plus alpha minus 1. Okay, now so we can actually bring that sigma squared in, which is equal to 1 over n plus sigma squared over alpha. Yeah? So in other words, the mean mu is actually equal to 1 over n plus sigma squared over alpha of sum of ti minus mxi, I equals 1 to n. So that's really similar to the estimate, the frequentist estimate you get. And in fact, you can see there's two things that could happen. If sigma was infinite, your prior variance was infinite, then this term would be 1 over n. Now, you're not allowed to have an infinite prior variance because your posterior, what effect does that have? If you have an infinite prior variance, then you can end up with basically an unnormalized posterior. So if you only have one observation, it turns out that you don't actually get a posterior distribution that's normalized. But you can look at that limit. It's an interesting limit. So as alpha, as the variance of the prior goes large, you start to recover the maximum likelihood solution matching the mean of this distribution. The other thing that can happen is if the noise variance is 0, so if there's no uncertainty, you also recover the same mean. So that is actually, that's quite interesting what that means physically in the one-dimensional case. Well, we can even draw that. I'm just making this up as I go along, so I hope this is right. So if you just have one observation, and let's ignore mx, let's just assume m0 for this case. If you have one observation, if the noise variance was 0, then all data would have to go right through that point precisely, which would mean the intercept, the average intercept in the posterior was going to be exactly where that point was. Yeah? So that's happening in the case where the noise variance is 0. Yeah? You basically recover that the intercept is there on the axis. However, the variance in that case, if the noise variance was 0, is also a bit messed up. Okay, won't go into that. So anyway, there's this relationship between the mean of the posterior and the maximum likelihood estimate. And that's very, very common. We'll see it in the multivariate case as well. But there is this slight difference that we're sort of, this is actually, turns out to be a bit like a regularizer. We call this a regularizer. Another interpretation for this can be that it's like having, that if this is like observing an additional data point, because this is a count of the data points, and this is adding something to the count of the data points. So if this was 0 in one case, so if you like had one observation where, if you had like an observation 0 where ti was equal to mxi, for example, so that observation was 0, but then you had a count associated with that observation there, that's like adding that in there. And that there's an interpretation about Bayesian inference from an information theory perspective associated with that. It's not part of this syllabus, but it's just there. Okay, so I think back to the slides. So that's actually the first lecture done, isn't it? Which I think is about right. Okay. Well, let's just cover this. We'll take it doesn't matter really when we take our 10-minute break. This is what I want you to sort of understand as what's going on as well. So there's two processes going here. This is very, very simple. You've got a prior distribution over this intercept parameter C, which I've drawn as a Gaussian along here. It's a function of C, but we can draw it as a nice Gaussian. That's a normalized Gaussian. Now, this is the likelihood. It looks like a Gaussian. It's unusual, the Gaussian case, because it looks like a Gaussian, but it's not a Gaussian in this value. It's a Gaussian in T. But T always appears next to C. So somehow it's an unusual case where it is like a normalized Gaussian, but most likelihoods aren't sort of normalized in these circumstances. But this one is. In general, that wouldn't happen. So there's the likelihood, and that comes from the observation. So in this case, it's saying there's an observation centered at 0.5. And what you do is you multiply the prior by the likelihood and renormalize. So you can see what's sort of going to happen is where they... Here red's 0, blue's 0, so that's going to squash that bit of the red. Here red is 0, so that's going to squash that bit of the blue. And indeed what you get is you get a little bump jumping up. Now because of some properties of this likelihood, the variance of this purple, the magenta, sorry, it's the combination of red and blue, will always be lower than the variance of red. Because of the properties of the Gaussian likelihood. So you renormalize that, and that's your new estimate. So that's like a one observation. In practice, you would now have multiple observations of T, and each one would cause you to, you could think of multiplying each one by this, the previous posterior, and you would update your estimate. So this is how you're expressing the uncertainty. You start with that being your belief, then you make an observation, you move the mean, and you reduce your variance. That's the process of Bayesian inference. As you gain information, you reduce the level of uncertainty you have about your data. Okay? So that's in one dimension. Take a break now. And after the break, we're going to talk about basis functions and multivariate regression. Okay? So back here by, well, in 10 minutes, which is 5 past by that clock. I don't know if that clock's right.
Carsten and I gave that, I was going to ask you this earlier. So Carsten and I gave that sort of talk to the group on Wednesday by Gaussian process. It went really well, like got some positive feedback and whatever. But the only thing